Let's start the topic fracture mechanics. Now, objective of this topic is initially we are going to define what is fracture and its types. Then we'll see the mechanism of ductile fracture, and then we'll see the mechanism of brittle fracture, the famous Griffith Criterion, and then we'll learn the concepts of stress intensity factor and fracture toughness, and how with the help of these concepts we can predict fracture in a component. That we'll see through some problem solving. Now, the definition is that the separation of material in two or more pieces in response to a remotely applied load. So this is what is the definition of fracture. And if we at least try to differentiate the fracture from cutting, then we can say in case of cutting also a material is divided into number of pieces. In fracture also the same thing occurs. They are divided in or separated into two or more pieces. But in case of cutting, what is happening, the material is separating at the point where the load is applied. On the other hand, in case of a fracture, it is a remotely applied load, so where the load is applied but the material is separating maybe away from that point. So this is what is the definition of fracture. The fracture can be of two types, ductile fracture and brittle fracture. Okay, remember one thing, that ductile fracture, brittle fracture, these things are not very much material specific always. It can depends on the type of loading also. That means if the loading rate is very high, it may be possible that a ductile material fracture in a brittle way. So brittle fracture is also possible in a ductile material if the loading rate is very high. So let us try to understand at least the mechanism of the fracture first. Now first we'll see the mechanism of the ductile fracture, how ductile fracture occurs. Now in case of ductile material which are free of any impurities, which is very ideal, but if it is possible that we can make very pure ductile material, then if we put that sample under tensile testing, we will find that the fracture is taking place like this. So here you can see almost 100% area reduction is observed. Okay, but these things are very rare. These are possible only if there is no impurities present in a purely ductile material. Okay, highly ductile material, there is no impurities present. But in commercially available ductile materials that we generally put as a sample in our tensile test, we will find that the typical ductile fracture look like this. Okay, so let us see that how this fracture occurs, or what is the mechanism of this kind of ductile fracture. So here you can see the steps of the ductile fracture. Okay, so if you see that fracture occurs, you know that after nicking in the sample. The sample is put under tensile test, and here you can see the nick formation started. That means a particular section where drastically cross-sectional area is reducing. The next stage you will see that there are some cavity that is formed within the material. Here you can see few cavities are formed in that region, where in that section where nicking started. Now how these cavities are forming, that can be explained in that way. If you see what happens, that if some impurity is present within a ductile material, let us consider this is an impurity particle which is present very small within a ductile material, and suppose the ductile material sample is like this, which is put under tensile test like this. Then what is happening because of this load, the material, the soft ductile material, which is surrounding this impurity, generally these impurity are very hard, they are very hard and brittle material. So because of the loading, the surrounding ductile materials actually yields and they actually deform. But this one, that means the impurity particle being very hard, are not actually yield, and that's why what happens, a cavity is forming surrounding that particle. Okay, so this phenomena is actually responsible for creating this kind of cavities or microcavities in that section, because of the presence of this kind of impurity particles within the material. Now in the next stage, you can see these cavities now get together and they form a larger cavity, and which is in the form of crack. Okay, so here you can see the crack formation, and then with the application of load, gradually this crack propagates. But since it is a ductile material, the propagation is very not so fast, and it is gradually propagating across the section. And finally here you can see that this ends, after this region here you can see the crack is propagating, and at this range basically the shear failure occurs at the surface, near to the surface, and you know that the maximum shear occurs at the 45-degree angle, and that's under tension. So close to the surface there is a 45-degree angle you will observe, and in the major portion of the section you will find it's a fibrous kind of a surface, fracture surface. And the reason is because of this kind of cavity formation and all that, and the crack propagating that way, and finally it fractures. So this is what are the different steps that happens in case of a ductile fracture. And here you can see one picture of a ductile fracture of mild steel sample, and here you can see a typical cup and cone formation occurs. Okay, so as if this is a cone and this is a cup, so this kind of ductile fracture is called a cup and cone fracture. Okay, this is very common, and I have already explained that why this region, the fibrous region, you will observe, and at the near to the surface it's a 45-degree angle that you will observe because of the maximum shear in case of a ductile material. Okay, so this is what is the observation in case of a ductile fracture. Now coming to the mechanism of brittle fracture. Okay, so brittle fracture is very dangerous. If you compare with respect to ductile fracture actually takes a long time before fracture, because a lot of plastic deformation takes place before fracture. But in case of a brittle fracture, since yielding is hardly observed, so what happens, that fracture is taking place almost in no time. Okay, and here you can see in case of a tensile test, you can observe if there is any crack, that crack propagates perpendicular to the direction of the load. So this is the load direction in a tensile test sample, and you can see this is the fracture surface, very smooth fracture surface. Okay, and this is how the fracture occurs in case of the brittle material, and a catastrophic fracture occurs. Suddenly the fracture occurs before any initial indication. That's why brittle fracture is very dangerous. Now we'll see that what is the criteria and how can we predict initially or from the sample condition, crack and all that, the fracture will occur, or how the fracture can be predicted. So fracture in case of can be of three modes. You can see in the mode 1 you can see it is the tensile load. If you apply, then because of that the fracture will propagate. That means the crack will propagate and the fracture will occur. Okay, so if there is a crack and the load is tensile, then perpendicular to the direction of the load, the crack will propagate. Here you can see the crack is propagating in the same plane, in a shear on the same plane because of shear, and this is called a sliding kind of a mode. And here you can see the tearing kind of a mode. This is also shear, but this is a cross plane shear, and this is a sliding. This is kind of a tearing. But the most important one, that means from the design point of view, that is the mode 1, because this is very common and most dangerous, and for this basically large amount of loads are required, and that's why we generally design based on mode 1. Now if we see, if we try to see what is the basic mechanism behind the fracture that is taking place in case of a brittle material, here you can see under tensile load what happens. There are basically atoms here, and they are connected by the bonds, right? So to propagate this crack in this material, this bond has to break, right? And then only this bond has to be break, and then only the crack will propagate. So I hope you can understand what I mean to say. Okay, so if you apply load, and if the load is sufficient so that it can overcome the bond strength of the atoms along the length of the crack, then only the crack will propagate, right? So from the theoretical study, it can be predicted that the cohesive strength is basically the bond strength, that the attraction force among the same atoms within the same material. So that is in the order of E by 10. Okay, so E by 10 is the strength in the bond, but it has been observed experimentally from the tensile test, you know, that brittle material cracks at the stress level which is in the order of E by 1000. That means at a much lower stress level, material actually fractures. Okay, whereas you see that the stress that is required to break the bonds are quite high. Okay, then why this observation is coming, that at a lower stress value the material actually fractures? The reason is this, because the cracks or flaws are present always in the material even before it is in service. That means cracks and flaws these are always present during the manufacturing of a particular component, during its handling, during its service. So cracks are coming in the material, and it is not possible that a material without any crack. Okay, so cracks are always present within the material, and this is the reason that this, because of the crack, let us consider this elliptical crack is present in this material. Then what is happening, that at the tip, at this region or at this region, because of the stress concentration, the stress, maximum stress is very, very high, and it is almost 100 times or more than that and this particular stress. And here you can see at the tip the stress is very, very high, and that's why what is actually happening, even though this value is quite low, but the material fracture because of the presence of the crack. Because of the crack tip, the stress is raising to a very high level because of stress concentration, and that value is in the order of E by 10. That means the stress required to break the bonds, and then the crack will propagate. So this is what is the criteria. Okay, that is the reason that why at a small load, at a small stress, material actually fractures. Reason, this one is small, but because of the presence of crack or flaws present within the material, at the tip of those crack or discontinuities or flaws, stress is very high, and because of that bonds are breaking and finally fracture occurs. That means the cracks are propagating throughout the material. So this is what is actually happening. Now let us try to understand that what is the value of this maximum stress. We have seen that the maximum stress will be developed at the tip of the crack. Okay, so what will be that maximum value of stress? That can be found out from this expression. Okay, so here this is the maximum stress that will occur at the tip, and that will be equal to 2 into nominal stress into A. A is, here you can see, if it is internal crack, then the half of the crack size. Here you can see the total crack size of the crack length is 2A, so A is basically half of the crack length, right? And if it is a surface crack, here you can see, if it is a surface crack, then A is the crack length. Okay, so for internal crack, A is half of the crack length. For surface crack, A is the crack length. Okay, so this A divided by the radius of curvature at the tip. Rho T, T indicates tip, rho is radius of curvature. So here you can see at the tip, here you can see, so this is what is the radius of curvature of the tip. So from this formula actually we can find out what will be the maximum stress that will be developed. Actually this formula is like this: sigma m is equal to 1 plus 2 into square root of A by radius of curvature into nominal stress. This is actually the formula to finding out the maximum stress. But if the rho is very small and A is very long, that means for a very fine crack, so the crack is like this. Okay, so these are commonly we find this kind of a crack where the radius of curvatures are actually very small. If you see the order of magnitude, they are very small. So if radius of curvature is very small and A is very large, then what will happen? This quantity will be very large. Okay, if this is very small and this is large, then this quantity will be very high. So that quantity, then with respect to this quantity, one can be ignored, and that's why the expression in this expression, basically this one is ignored and it is written like this. Okay, so maximum stress we can find out in a material if we know what is the nominal stress that is acting. Okay, so we have seen that how can we find out the maximum stress. Next question is, okay, we have understood the maximum stress, but what is the criteria that for which the crack will propagate? The crack will propagate if this maximum stress is more than or equal to some value of stress, some critical stress, it is more than some critical value, then crack will propagate. Okay, so the stress will be maximum, and we have to find out that what is this critical value above which if the maximum stress increases, then it will propagate. Now to find out this critical value, the stress, if the stress is more than this critical value, then it will propagate. Okay, let's see how to find out this critical value. Okay, so here you can see a guideline that how can we find out this critical value, and that is what is called the Griffith's theory of brittle fracture. So sigma c that is the critical value, can be found out from this equation. Okay, so where from this is coming, that is basically the energy criteria, and from that energy criteria this can be derived, that the value of the critical value of that stress, if the stress is more than that value, then crack will propagate or crack will become unstable, so it will catastrophic failure of the material, fracture will occur in the material. But remember, this Griffith's criteria is for the brittle material, okay, where E is the modulus of elasticity in this expression. This gamma S is the specific surface energy, that means surface energy per unit area, and A is half crack length for the internal crack. Okay, so now let us see that how this expression is coming, or what is the criteria from which this has been derived. Okay, so this has been derived from the Griffith's criteria, where according to this criteria a crack will propagate when the decrease in elastic strain energy is at least equal to create the new crack. Now let us try to understand this thing first. Now see, if you consider this is a sample, if you consider this is a sample and which is under tension, okay, and consider this is a crack of length 2a, okay. Now if we draw the flow lines from one end to the other end, you know that the stress flow lines are continuous lines. That means they are starting from one end and coming to the other end. And if there is no crack, then these lines will be exactly parallel from this end to this end. But if there is crack like this one, forget about this one for the time being, okay, forget about this one. And in this crack, around the crack, if you see how the flow lines will pass, so it will pass like this. Okay, or here you can see they will pass like this. Okay, so these are the flow lines will look like this. We just ignore this particular thing right now. Suppose this is the material and ignore it. Okay, suppose there is no crack present here, just ignore it. Only this internal crack is there. So this will be the stress flow lines that will pass from one end to the other. Now gradually when you are applying the load, then what is happening, basically the material is straining, okay, the mechanical strain will be developed within the material, elastic strain will be developed within the material, okay. Now because of that, what will happen, the strain energy will be stored within the material. So within elastic limit, what will happen, if the material strain, the strain energy will be stored, elastic strain energy will be stored within the material. Now you just compare that, suppose there is crack and there is no crack. In these two situations, what will happen? If there is crack, then you observe in this region, you observe this region, let us take some color, okay. Let us observe in this region, almost this region, sorry, region actually look like this. So in this region there is no stress flow lines. That means there is no strain energy stored in this volume. In this region, no strain energy will be stored. That means if you compare with respect to the material where there is no crack, with respect to that, this material where crack is present will release some of the strain energy corresponding to the strain energy in this region. Okay, so how much strain energy will be decreased if there is any crack? So that we can estimate. So what will be that? That will be, you know what is the expression of strain energy? It is half into stress into strain. That is strain energy per unit volume, right? If you multiply it by the volume, then you will get what is the amount of strain energy. Okay, so this is elastic strain energy, U elastic, not the mechanical strain energy, right? Elastic strain energy. Now let us take red color to look at it. Okay, now this is elastic strain energy. Now what we are doing, we want to find out how much energy will be changed if there is no crack and if there is crack. So how much strain energy will be released? The strain energy that will be released if the crack is present is half. So energy released will be half into stress into strain into the volume. What is the volume? So volume in this region that will be released because of the crack. In this region, how much strain energy can be stored? That will be released. And that strain energy, so that is what is the first point. Crack will propagate when the decrease in elastic strain energy. The first part now we are calculating. Okay, so how much strain energy will be released, that we are calculating. So what is the volume of this portion? The volume of this portion, we are not going to do all the geometry, but we are using this. You can thought of a circle of diameter 2a or the radius a. Then this portion is still there, right? This portion is still there. So what is the idea? You just consider twice of the circular area. That means pi a square is for this portion, and for the remaining portion, that summation of these two portions is also again another pi a square, another circular area. So total area of this shape, is approximately equal to 2 pi a square. Okay, so what is the volume? If that length in the perpendicular to the screen is L, then this multiplied by the L is basically what is the volume. So this much of energy will be released. Since it is released, so energy will decrease, so it is a negative sign. Okay, so this is what is UE. This is what is UE, or the change of strain energy, elastic strain energy, right? Now, because of the formation of crack, what will happen? Because of the formation of the crack, when the crack will propagate, that means when if the crack gradually grows, then what is actually happening? The new energy is required because the new surfaces are now developing. What is happening? If there is no crack, no new surface was there. But if there is crack, you just observe. If there is crack, now new surfaces are generating. So this is one surface, that means in perpendicular direction, and another surface at the bottom perpendicular to the. So new surfaces are generating. So to propagate crack, the surface energy is required because new surfaces are producing. So who will provide that energy? Obviously that energy will come from this energy released by the strain energy. So because of the applied load, some strain energy will be released and that strain energy can be used to form these new surfaces because of the crack. So surface energy that is required, surface energy that will be new surface energy US. You can write US. So what will be that US? US will be equal to what is that area? First of all, calculate that. Let us consider gamma S is the specific surface energy. Okay, this is specific surface energy. That means surface energy per unit area which is required multiplied by the area. What is the area? So approximately this length from here to here is 2a, right? This length is 2a. So it is as if this length perpendicular to the screen is L and this is A. So it is as if the top surface is A into L and the bottom surface is, this total length is 2a, 2a. So 2a into L, as if this rectangle, because this is very thin. So you can consider this is 2a multiplied by L. Okay, so 2a into L, that is the top surface, and at the bottom surface that is again 2a into L. So basically the total area is 4 into A into L. That will be required. These new surfaces, to develop these new surfaces, this much of energy is required, and this is positive. This is positive. Okay. So this one is negative and this one is positive. So according to this criteria, a crack will propagate when decrease in elastic strain energy is at least equal to create the new crack. So strain energy is at least equal to create the new crack. To create the new crack, the energy which is required is basically the surface energy. This energy is required. So energy released from this strain energy will be used to create this new surface. So now tell me that when the crack will propagate, when this strain energy is released is more than this surface energy, then crack will propagate, because this energy is large enough so that it can create the new surfaces. So it will create the new surfaces. That means the crack will propagate. So if this quantity is more than this quantity, then crack will propagate. This is what is the idea. Now this is basically done in this way, that what is the change of energy, whether it will be stable or unstable. We are talking about this, that whether the crack will be stable or unstable, right? So if the crack is unstable, then the crack will propagate, and if the crack is stable, that means the crack will be present within the material, within the component, but it is not going to propagate. Okay, so to do that analysis, what we are going to do is, let us find out the total change of energy. What is the total change of energy because of this energy released by strain energy and energy required because of the new surfaces? So that will be minus of half of stress into strain. What is that quantity? Half of stress into strain into what is that volume? We have considered that is 2 pi a square, right? 2 pi a square. And let us find out per unit length. Okay, so delta U per unit length. Okay, so pi a square, and we are not considering L. Okay, this quantity is negative. This quantity is negative. So now what we can write, instead of the strain, since it is within elastic limit for brittle materials, so sigma is equal to E into epsilon. So in place of epsilon, we can write sigma by E. So this expression will be what? Minus half sigma into sigma by E. Okay, into 2 pi a square which is equal to sigma square by E, sigma square by E into pi s square. So here you can see that expression. Okay, so this expression is corresponding to change of energy per unit length of elastic strain energy. There is another part. This one is the elastic strain energy part, and there is another part which is the surface energy. Again, the surface energy per unit length, that quantity, surface energy per unit length, that quantity will be 4A into gamma s. So L we have taken in that side. Okay, and this will be positive, and this quantity will be negative. Okay, so the total change of energy is then this plus this, and the criteria is ultimately it will be stable if the change is, that means if you draw this thing, what you will find is this. So if you plot the surface energy line, you will see this is how the surface energy is changing according to this formula. And if you plot the potential energy line, that means the elastic strain energy line, you will find this will follow this line. So total change of energy is what? This plus this. This is, remember, this is negative quantity, this is positive quantity. Okay, so this plus this, if you draw that graph, you will find this is what is the resultant change of energy, and here you can see that is the maximum. So this is what is the critical point. That means if you just plot the surface energy, you see here you can see the energy rate that has been plotted. Energy rate means this dA. This is what is the energy rate of the surface energy. Surface energy is what? That delta US. Okay, that we have considered. So that is 4 gamma s into A. Gamma s into 4A. So if you do that, you will get 4 gamma s. Okay, so this is this straight line. It is not changing with A. And if you plot this part, which is the strain energy part, which is the rate of strain energy part, rather rate of strain energy part, that means DDA, the rate with respect to crack length, DDA of this quantity, the whole quantity. If that is UE, then that UE. Okay, so that quantity is this. So if you differentiate this one, it will be 2 into something like that. Okay, so this quantity, its rate. So the criteria is that if the rate of strain energy is more than the rate of surface energy required, then crack will propagate, and that will happen at this point corresponding when this will be maximum. Okay, so how can I find out this maximum point? It's very simple. You just take the differentiation of these two and you just find out where is this point. And if you do that, this is a very simple exercise. You will end up with the solution that you found out is this one. Okay, so I think that is not required to be done, but still if you want, you can do that. This part will be 4 gamma s, and here the differentiation of this one will be what? Tell me. 2A pi sigma square by E, if you differentiate this one. So this is the point where these two will, that means this is the rate at which the surface is generating, surface energy is required, and this is the rate at which the strain energy is released. If this is more, if this quantity is more, then crack will propagate. That means this is the region where crack is going to propagate. This is the region that crack will be unstable, and this is the region that crack is stable. So crack becomes unstable after this region, and before that it is stable. Okay, so from there you can easily show that this sigma is coming what? 2E gamma S by pi A and square omega. Okay, so this is the same result what you can see. Okay, so this is what is the Griffith's criteria. From the Griffith's criteria, the criteria is the rate of energy release. Rate of energy released means, I think you have understood by the time, the rate, it means dDA. Okay, crack length with respect to crack size. So rate of energy release of the, if that is more than the rate of energy required to create new surface, then crack will propagate. Okay, so this is the critical value when just crack is going to unstable. Okay, now this equation is very helpful in finding out whether a particular crack size is unstable or stable. That means whether it will fracture or not. Okay, so to predict that fracture, this equation is really very helpful. And here just one problem I can tell you. Suppose there is 3 samples of glass, 3 samples of glass plates. Let us consider this is 1, this is 2, and this one is 3. Now in these 3 samples, can you tell me that which one will easily break? From your intuition, you know that this larger one is more prone to break if you compare with the other one, and this one is less prone to break, right? Because the size is small. The question is that how can you conclude mathematically that this is true? This is true because here you can see this is the parameter related to the crack size. So if the crack size is small, then the stress at which it will break is very large. Okay, so if you compare among these 3, in which one having the smaller crack size? No information is given about the crack size, but I have told you that crack will always be there during its handling, during its manufacturing. But it is for sure that crack cannot be more than its dimension. Okay, so it is expected that larger crack is possible in a material which is of the larger size. So larger crack will present in this kind of material, for this size, whereas obviously the smaller cracks are present in a smaller size material, a smaller size sample. So that's why the size of the crack definitely small in this case. So A is small. If A is small, then sigma C is large. That means it can take larger value of stress. Okay, but it will not be able to take larger value of stress because the crack sizes are large, so sigma C will be less. Okay, so now let's solve one problem. It's a very simple one. A relatively large plate of glass is subjected to tensile stress of 40 megapascal. So some sigma which is given 40 megapascal. If the specific surface energy and modulus of elasticity, these are given. Specific surface energy means gamma S, which is given 0.3 joule per meter square, and modulus of elasticity is given, that is 69 gigapascal. Remember, gigapascal is 10 to the power 9 Pascal. So question is determine the maximum length of a surface flaw that is possible without fracture. So you have to find out that critical A or the A max for which the fracture will just initiate. Okay, so we are going to use the expression from the Griffith Criterion, that sigma c is equal to what? We know 2E gamma s by pi A. Now see, in this expression, since we have to find out the maximum A, so that means when A is maximum, that we have to find out corresponding to this critical value, and that critical value in this case is 40 megapascal. Okay, so put that sigma as 40 megapascal, and E and gamma s, these are given. So from this equation you can find out what is the value of A max. So you can solve A max simply using this relation. It is as simple as that. Okay. Now another way of looking this thing, that means to predict the fracture, is the stress intensity factor. Okay, here you can see that I have already told you there are three different modes of failure. Here this one is the mode 1, where tensile load is applied, and this is the most vulnerable one, and that's why we are interested in this one. So let us first define stress intensity factor for the mode 1. So this one is the 1 corresponds to the mode 1. Okay, so it is symbolized by capital K. So stress intensity factor is, which is defined as Y into sigma, which is the nominal stress which is applied, into square root of pi into A. So this is what is the stress intensity factor, and if we know the crack size, if we know the load that is applied on the material, we can find out the nominal stress. And this one is a modification factor. This is a modification factor which depends on the geometry or the loading type. Based on that, this can be found out, and then it is possible to calculate the stress intensity factor in a particular sample. Okay, so the criteria for the fracture is that if the stress intensity factor is more than some critical value, then fracture will take place. Okay, so that's why, and this is a very important parameter that will help you to take decision that whether fracture will take place or not. So here sigma is very simple, the applied load or the nominal stress that you can easily find out. A is the crack size related to the crack size. Already you know that for internal crack it is half crack length, for the surface crack it is the crack size. And Y, how can you find out this Y? Y is a modification factor. To probably in exam this value will be provided, but in practical design this Y can be found out from the handbook data. Okay, let's take some of the Y values. Here you can see in the Y axis there is the Y value. Okay, the Y, the modification factor, and in some of the book you will find that this value is written as beta. Anyway, in decalister it is given as Y. Here you can see that it depends on the loading. Here you can see axial loading given on a plate, and this is a surface crack. These dimensions are there, and you see that different curves corresponding to some dimension ratio. X-axis also depends on geometrical ratios, so that means this Y value depends on the geometry of the crack and the relative geometry of the crack with respect to the plate, and also the type of loading. Here you can see another one. Here it is not a surface crack, it is internal crack, and again it depends on these geometrical parameters. Again, the type of loading is axial load. Here you can see the type of loading is bending, and the geometrical parameters if known, then from those geometrical parameters it is possible to find out what is the value of y. Okay, so these are some of the handbook data I have just shown you to understand that in practice actually how these y values are calculated. Here you can see another example where let us consider this is a pressure vessel, that some fluid at a very high pressure may be within that pressure vessel, and there is a radial crack you can see, and there also you can find out y depending upon the geometrical parameters. Okay. Now another very important thing that is critical stress intensity factor. I have just told you that the fracture prediction is done based on whether the stress intensity factor for mode 1, if that is more than some critical value, this C corresponds to some critical value, then the crack will propagate very fast. Okay, that means the crack will become unstable. Okay, so this is, remember, a material property. This is not a geometrical parameter and all that. This is a material property, this critical value, which is called the fracture toughness. This is also called the fracture toughness or critical stress intensity factor. You can give both the names. Okay, so critical stress intensity factor is a very important thing, and that will be listed again in the handbook corresponding to different temperatures, because this particular value changes with the temperature. This is a material property. It depends on the temperature, it depends on the loading rate or the strain rate, but it is not no way related to the crack and all that. That means it is not dependent on the geometry but on the material. That is the most important thing to remember. And K1, that is the stress intensity factor, that we have just seen, this quantity stress intensity factor, that we have to calculate based on the crack and the geometry and the load. Then we will compare with the fracture toughness or the critical value, and then finally take the decision whether material is going to fracture or not. Okay, so here some of the typical fracture toughness values we can see, and their yield strength values are also noted. So I have already told you that this critical stress intensity factor or the fracture toughness value, it is like some specific value depends on the material, and it is also depending on the temperature. Basically what happens that if the temperature is decreased, that means at a very low temperature, this value is generally decreased. Okay, so this critical stress intensity factor of the fracture toughness generally decreases with the decrease of temperature. So if temperature decreases, then K1C also decreases, because the reason is very simple, because if the temperature decreases, then material becomes more and more brittle. You know that at very low temperature, if the material is cold, then it will become more and more brittle, and then basically the fracture toughness critical value also decreases. Okay, that means at a lower value there is a chance that it crack can propagate. It also depends, K1C also depends on the strain rate. Fracture toughness also depends on the strain rate. That means here you can see a mild steel sample maybe, or some ductile material, if that is loaded gradually, then it will show this kind of a stress strain pattern. That means it's a highly ductile material. You can see a lot of plastic deformation. That means strain rate is smaller. That is the gradually applied load. This one is the strain rate, epsilon dot, the rate at which the load is given. Gradually the strain is taking place. But if the strain rate is very high, that means if suddenly load is applied, then the strain rate is very high, impact load, strain rate is very high. Okay, so for those cases, you see the very ductile material is giving this kind of result. That means it is behaving like a brittle material. The same material, depending upon the strain rate, when it is larger, is behaving like a brittle material, and that's why what happens, the fracture toughness value actually decreases. Okay, so these are some things which are very important. Now let us try to solve few problems related to that. Problems are not very difficult, just you have to understand the concept. An aircraft component is fabricated from an aluminium alloy that has a plane strain fracture toughness 40 megapascal. So what is given? That is K1C. This value is given. Critical value, that means the fracture toughness, that is given 40. Remember, the unit is not the unit of stress, it is unit of stress multiplied by square root of length. Okay, then it has been determined that fracture results at a stress of 300 megapascal. It has been observed that fracture takes place at 300 megapascal. When the maximum internal crack length is 4 mm, corresponding to maximum internal crack length is 4 mm. 4 mm. And for this, the same component, an alloy, will fracture occur. This is the question: will the fracture occur at a stress level 260 megapascal and the maximum internal crack length is 6 mm? Now loading is different. Loading has been changed to 260 megapascal, which has been reduced, but now the sample having larger crack length. Now the sample having larger crack length, say A prime, and that is 6 mm. The question is, tell me, under this condition the fracture will take place or not? This is what is the question. So actually what we do, we will first write the expression that what is the condition, you know, the critical condition, that is if KIC is equal to what? When the fracture just occurs corresponding to a maximum crack length, then it will become Y sigma root over pi into A. When this A will be maximum, this will be the critical value, and then this will be the fracture toughness, that is the critical condition. Now K1C is given, sigma C, that is this one which is known, A max, that is known. So from this expression you find out what is the Y. Okay, since the every conditions are remaining same, so what you can do, you just find out, write the same equation and find out what is the K1 stress intensity factor and check whether it is more than fracture toughness or not. So what is K1? It is Y. Put the same Y that you got from the first part of the problem. Use this sigma prime, this value, into root over pi A, and use this value. Okay, so now you know Y, because Y already you have calculated from the first part. Sigma prime is given, A prime is known. Find out what is K1. Now if this K1 is more than or equal to K1C, then fracture occurs. If this is, then fracture occurs. Then fracture occurs. Okay, so if not, then fracture will not occur. Okay, so this is how can we solve the problem. How we can now the second problem, the critical stress intensity of a material for a component. Critical stress intensity for a material for a component of a design is this. So which one is given? The fracture toughness critical value, that is known 22.5 kilopound per square inch √inch. What is the applied stress that will cause fracture if component contains an internal crack 0.12 inch? So A is given, component contains an internal crack of 0.12 inch long. So what is the length of the internal crack? So here one thing you just observe in the last problem we have discussed, internal crack length is 4 millimeter. See, internal crack length is 4 millimeter, but A is not 4 millimeter. If you remember, what was the dimension of the crack length? So from here to here, that length was 2A. This is what is the crack length, right? This is what is the crack length. So actually A is 4 millimeter divided by 2. Okay, A is basically half of the crack length if it is an internal crack. Now here also, if A prime is not 6 millimeter, because the maximum internal crack length 6 millimeter, that means A prime is 6 millimeter divided by 2. Okay, so please take care of this correction. So here also, what is A? 0.12 inch long internal crack. That means A will be equal to 0.12 divided by 2, because it is internal crack. Okay, if it is a surface crack, then that will be the value of it. So 0.06 inch. This is what is it. And the problem is you have to find out the applied stress for which it will propagate. So use the same formula, because that means in this case Ki is equal to Ko, because since it is propagating at that value. So that is Y into sigma √/U. So Y, you just take 1. Sigma is, you have to find out K1C, that already you know what is A, so you can find out the value of sigma. Okay, now for this one, what is the largest size internal crack that a thick plate of aluminum alloy can support at an applied stress of 3/4 of the yield strength and half of the yield strength? Okay, assume Y is equal to 1. Okay, so for this also we are going to use the same formula. Only thing is that what is given, this is the material, and material means this is what is the material. So corresponding which the data that we have to consider in inch. So let us go. This is one of the data, that means the fracture toughness, and yield strength value is this one, 83. So what is the applied load? So applied load is given 3/4 of the yield strength. That is the first part of the problem. So 3/4 of the yield strength, and that yield strength is what? 83. Okay, so you know what is sigma. What is Y? Y is given 1, and the fracture toughness is 21. So write the formula. So K1C, because this is again the situation when just it is going to propagate. So Y sigma √πA. where K1C is basically 21, that is the fracture toughness. Y is given 1, Y is 1, Y is sigma is 3/4 of SY, where SY is 83. So you can find out the largest size internal crack. So what will be the largest size internal crack? So crack size will be 2A. Remember, you can find out A, but the crack size is twice of that. It is internal crack, so it will be twice of A. So crack size will be twice A. So do not make that mistake. So that is as simple as that. Okay. So this much for today.